Hello everyone. Today we start with the topic of sequential circuit, that is counters. The objective of this video is to know about various types of counter, classify into its types, design a counter as a finite state machine, and see what are the applications. So first let us see what is a counter. As I said, it is a sequential circuit and it is a device which stores or displays the number of times an event has occurred. Now that event is basically in relationship to a clock signal. So we use counters in digital electronics for the purpose of counting. They are used for counting the number of clock cycles. Classification of counters is basically as asynchronous and synchronous counters. Let's see what are asynchronous and synchronous and find out the differences between the two. So in asynchronous counter, we apply the clock signal only to the first flip-flop. The output of the first flip-flop goes as clock to the second stage. The output of the second stage goes as clock to the next, and so on. Whereas in synchronous counter, there is a single global clock which drives all the flip-flop stages. Because of this, the output changes in parallel in case of a synchronous counter. Coming to the third point of difference, in asynchronous, we are going to use T flip-flops, and even if other flip-flops are used, they have to be converted into T flip-flop and then used in the design. Whereas in case of synchronous counter, we can use any type of flip-flops. Next, the speed of an asynchronous counter is dependent on the number of bits used for the flip-flop. Whereas in case of synchronous, the speed becomes independent of the number of flip-flops used. An advantage of asynchronous counter is that no extra logic gates are required, whereas in case of synchronous counter, logic gates are required for the design. Because of this logic gates, which is not required in asynchronous counter, the cost becomes less, whereas for synchronous counter, the cost becomes more. Let's see the design of asynchronous counters. We start with the design of a 2-bit asynchronous counter. Now, a special worth mentioning term over here is ripple counter, which is synonymous to asynchronous counter. The terminology arises from the fact that in case of a asynchronous counter, the clock goes only as input to the first flip-flop, whereas the output of first stage goes as clock to the second. The output of second stage goes as clock to the third. Hence, the propagation of clock pulse is in the form of ripples, from which the name comes as ripple counter. So, the diagram over here shows the logic diagram for a 2-bit ripple counter. As you can see, it is made up of two T flip-flops, namely TA and TB. Both the T flip-flops are connected to logic 1, or we can say that they are configured to be in the toggle mode. The external clock is applied only to flip-flop stage A, and the output of A goes as clock to the next flip-flop, that is flip-flop B. To understand the operation, initially let us assume that the output of both flip-flops are 0, 0, that is QA QB equals to 0, 0. As soon as the first negative edge of the clock comes, flip-flop A will toggle, and hence QA will become 1. So the transition of QA is from 0 to 1. That is a positive edge, and hence flip-flop B will not show any transition in its output. Therefore, at the end of first clock pulse, QB QA is equal to 0, 1. Now, when the second negative edge of the clock comes, flip-flop A will again toggle because it is receiving the clock directly. So QA will change from 1 to 0. A transition of 1 to 0 in QA acts as a negative clock pulse for flip-flop B, and as TB is connected to 1, it will toggle now from 0 to 1. So, after the second clock pulse, the output QB QA equals to 1, 0. Now, after the third clock edge has come, A will again toggle and it will become 1 from 0. So a 0 to 1 transition of A will not trigger flip-flop B, which will remain at state 1. So what is the output of after the third negative edge? It is 1 1. After the fourth negative edge, flip-flop A will again toggle. So flip-flop A toggles with every arrival of clock pulse. It will change from 1 to 0. A 1 to 0 transition of A will trigger B, which will also toggle from 1 to 0. Therefore, after the fourth clock pulse, the output of the counter is 0 0. This we can understand from the truth table of the 2-bit ripple counter, which has been shown here. So initially we have assumed that QB QA equals to 0 0. After the first clock pulse, A is toggling from 0 to 1. After this transition of A is not affecting B. So the output after the first clock pulse is 1. Now on the second clock pulse, QA is again toggling, and this negative transition of QA is changing QB, which becomes 1 from 0. So the count at the end of second clock pulse is 2. After the third clock pulse, A is again toggling. This positive transition of A does not affect B, so it remains at 1. The count state after the third clock pulse is 3. After the fourth clock pulse comes, A will again toggle. This negative transition of A will trigger B, which will change to 0. So we see that after the fourth clock pulse, it again goes back to the initial count, that is 0 0. So what are the count states received or achieved by this 2-bit triple counter? 0, 1, 2, 3, and then back to 0. So with 2 bits we are getting 4 distinct states of the counter. Next we see the design of a 4-bit ripple counter. In a 4-bit ripple counter, the design is done using JK flip-flops. As we can see, both the J and K inputs are tied together. When we short the J and K inputs like this, it acts as a T flip-flop. And all these T inputs are connected to logic 1, so they are set to toggle. The clock which we are using over here at the first flip-flop stage is a positive edge trigger clock. The output of the first stage goes as clock to second. The output of second stage goes as clock to the third, and so on and so forth. Now initially we assume that all the flip-flops are at 0 0 0 0. On the first clock edge, only the LSB bit is changing, because this Q0 flip-flop is receiving the clock pulses directly. Now this positive change of Q0 is not affecting Q1, which remains at 0, and hence the remaining outputs also is unchanged. Now when the second clock pulse comes, Q0 again toggles. So basically Q0 will toggle with arrival of each and every clock pulse. Next, when Q0 changes from 1 to 0, Q1 is triggered from 0 to 1. This positive transition of Q1 does not affect Q2, which remains at logic 0, and hence Q3 also remains at logic 0. On the third clock pulse, Q0 is again toggling, which is a positive edge for Q1. Therefore Q1 remains unchanged, and hence Q2 and Q3 also remains unchanged. On the fourth clock pulse, Q0 changes from 1 to 0. This negative transition of Q0 will affect Q1, which also changes from 1 to 0. Now this negative edge of Q1 acts as a clock signal for Q2, which now toggles from 0 to 1. As this is a positive transition of Q2, hence Q3 does not change. So and so forth. If you go on applying successive clock pulses, we see that after the 8th clock pulse is given, Q2 makes a negative transition, which will trigger Q3, which will now toggle from 0 to 1. So the count states which are attained are from all zeros to all ones, after which the counter resets, which happens on the 16th clock pulse. So a 4-bit ripple counter will count through 16 states starting from 0 0 0 0 to 1 1 1 1, after which it will reset itself. Next we move to the design of synchronous counters. In synchronous counters, as we have seen in the different slide, the clock pulses are applied to all the flip-flops simultaneously. So one advantage which we get in synchronous counter as compared to asynchronous counter is that it can operate at higher frequency. Why? Because the same clock is given to all the flip-flops. QA and QB output of both the flip-flops is 0. After the first negative edge, QA will toggle and it will become 1. So the change of QA is from 0 to 1. But at the instant of application of the clock pulse, QA was 0. So since JB and KB was 0, flip-flop B will not toggle when the first clock pulse has arrived. This happens because of the finite propagation delay which happens inside flip-flop A. Because of this propagation delay, at the instant of arrival of the clock pulse, which was common for both flip-flops, QA had not toggled from 0 to 1. It was still at 0. That is why on the first clock edge, flip-flop B is not going to toggle. It will remain at logic 0. So output at the end of first negative clock edge is, for QB QA is 0 1. Now when the second clock pulse arrives, flip-flop A will again toggle, this time from 1 to 0. But QA output at the instant of application of clock pulse was 1. So flip-flop B will now toggle, it will toggle from 1 to 0. So the output at the end of second clock pulse is 1 0. At the third clock pulse, A will again toggle. This time it will toggle from 0 to 1. But since it was at 0, so flip-flop B is not going to toggle anymore. It will keep its output fixed at 1. So the output after third clock pulse is 1 1. On the fourth clock pulse, the counter will reset itself. So the counter has gone through 4 count states starting from 0 0, 0 1, 1 0, 1 1, after which it will reset itself. Now we go ahead with 4-bit synchronous counter using 4 JK flip-flop stages. As you can see, the JK inputs of both flip-flops are tied together and hence they are configured as T flip-flops. But the difference over here is that the Q output of first stage goes as JK input to the next. The Q outputs of the previous 2 stages logically ANDed goes as T input to the third, and the Q output of all the previous stages, that is Q0, Q1 and Q2 ANDed together goes as JK input to the fourth stage. So every successive stage is receiving the Q output of all the previous stages. As it is a synchronous counter, we can see that there is a common clock input going to all the flip-flop stages. To understand the operation, let us see the waveforms. Initially, we have assumed that Q0, Q1, Q2, Q3 are all at logic 0. On arrival of the first negative clock pulse, Q0 is toggling. In fact, Q0, because it is the first clock stage connected directly to the clock whose input is set to VCC, this is ready to toggle with each and every negative edge of the clock that comes. So with each and every negative clock edge, you can see in the waveform Q0 is toggling. Now Q1 will toggle when the negative edges of Q0 occurs. So basically the frequency of Q0 is further divided at Q1. Q2 will toggle when the negative edge of Q1 comes. So frequency gets further divided down, and Q3 will toggle when the negative edge of Q2 comes. So the frequency is further divided down. Now if I count this output with each and every clock pulse, we start with 0 0 0 0. After the first clock edge, the count becomes 0 0 0 1. After the second clock edge, the count becomes 0 0 1 0. After the fourth clock edge, it becomes 0 1 0 0 and so on. So basically we are counting the number of clock pulses which are applied to this circuit, and hence we get a 4-bit synchronous counter giving me counts starting from all zeros to all ones, after which the counter will reset itself. Now We can also classify the counters, whether it is synchronous or asynchronous. We can design up counters as well as down counters, and in fact we can also get an up down counter in the same circuit. Up counters was achieved by connecting the QA output of one stage as the clock to the next. In case of down counters, we are going to connect the Q bar output of one flip-flop to the clock input of next stage. So what shall we do in case of up-down counters? In case of up-down counters, we are going to use an extra input which we call as the mode control bit. That mode control bit gives us an option to select whether we want to count up or go in the reverse mode, that is in the down mode. For this, we require an extra combinational circuit which will be designed and used between each pair of flip-flop in order to achieve that up-down operation. So we go ahead with the up-down counter design. We are going to use flip-flops depending upon the number of count stages we require, and all the flip-flops will act as in the toggle mode. That means we are going to use either T flip-flops or JK flip-flops. The LSB flip-flop will receive the clock directly, but the other flip-flop stages will receive the clock from the previous stage. For up mode, it will get the clock from the Q output of the preceding stage, whereas for the down mode, the Q bar output of the preceding flip-flop will be connected to the next stage. We go ahead with the design of a 3-bit binary up-down ripple counter. As I said, since it is 3 bits, so 3 flip-flops are required. As it is up-down counter, will require a mode control input. Now, since it is a ripple counter, the Q output of preceding flip-flop will be connected to the clock input of the next case for a up counter, whereas the Q bar output of the preceding flip-flop is connected to the clock input of the next stage for a down counter. The selection of Q and Q bar output will be controlled by this mode control bit M, so that if M equals to 0, we can get up counting, and if M equals to 1, we can get down counting. This is the block schematic for that up-down ripple counter. Depending upon the mode control bit, either Q or Q bar is gated to the clock of the next flip-flop stage. So, if I see the truth table, if the mode control bit M is 0, I am connecting Q output to the clock of the next stage, and Y becomes equal to Q for the up count, and Y becomes equal to Q bar when mode control bit is set to 1, that is for down counter. The circuit diagram and the waveforms are shown in this slide. Now, to understand the operation, initially let us say that M equals to 0. Here M is nothing but this up down bit. So, setting this bit to 0 disables AND gate, upper AND gates, whereas enables the lower AND gates. Since the upper AND gates are disabled,